In this video, we're going to start talking about stoichiometry. I'm going to give you a little bit of a background to stoichiometry, and I'm going to teach you how to do mole ratio problems, since that's the fundamental part of a stoichiometry math problem. If you take a look at the definition, it says that stoichiometry is the calculation of quantities of substances involved in chemical reactions. The key word there being quantities. So we just spent quite a bit of time learning about chemical equations and writing chemical equations on paper. Now we're going to apply the mathematics to it, and that's what we call stoichiometry. We always start with a chemical equation, and again, that's why we do chemical equations before we study stoichiometry. But the chemical equation can tell us two things. The first thing a chemical equation can tell us is how much reactant is needed to produce a given amount of product. So, for example, if I start with 10 grams of reactant A, how much of a particular product can I make if I have 10 grams of reactant A? The second thing the chemical equation tells us is the amount of one reactant needed to react with a given amount of another reactant. So if I start with 10 grams of reactant A, how many grams of reactant B do I need to go along with that? Those are called limiting reactant problems, and that's something we'll get to a little bit later in this part of the unit. These notes are in your packet, so if you haven't figured that out already, you can get them out and kind of follow along and take the notes as we go. The next thing we need to talk about is a mole ratio. And a mole ratio is a conversion factor that relates the number of moles of any two substances involved in a chemical reaction. So again, you've heard the word conversion factor before. That's important. That's going to be the same thing we were talking about prior with conversion factors. We said it relates the number of moles of any two substances involved in a chemical reaction. So if you look at this example reaction here, we have a decomposition reaction in which aluminum oxide is decomposing into aluminum and oxygen gas. And if you notice, the coefficients here are 2, 4, and 3. So when we call this a mole ratio, where we get the mole ratio from is from the coefficients. So I could say that for every 2 moles of aluminum oxide that react, I can make 4 moles of aluminum. Do you see how that kind of looks like a conversion factor that we would have used prior in this class? Another mole ratio that I could do is I could say, all right, well, if I have 2 moles of aluminum oxide react, I can make 3 moles of oxygen gas. So again, I'm just using these coefficients to make a ratio out of it. That's all a mole ratio is using the coefficients to make a ratio. The third mole ratio I could get from this problem, I could say that for every 4 moles of aluminum that form, 3 moles of oxygen gas will also form as well. So we have 3 different mole ratio systems that we can get from this one balanced decomposition reaction. All of these mole ratios can be flipped over depending on how you need your units to cancel, and you'll see how that works when I show you some examples, which we'll move on to right now. Okay. So again, just a little bit more background on stoichiometry. It says when doing problems, first make sure you have a balanced equation to work with. It's always important to first look at the equation and make sure it's balanced. Sometimes you're going to have to write it. And then the second tip is begin with the information given and work toward what the problem asks for, canceling units along the way. That should sound familiar. That's what we did when we did mole conversions in the last unit. So the first practice problem looks like this, and it gives us an equation at the top. Okay, it says carbon dioxide plus lithium hydroxide makes lithium carbonate and water. And if you notice this 2 right here, that kind of gives you a clue that the equation is probably already balanced. So we can kind of glance at that and double check just to make sure, and it looks like everything's balanced there. So the question says, how many moles, so put a little question mark there, how many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide? So I'm starting with 20 moles of carbon dioxide. How many moles of lithium hydroxide do I need to react along with that? And some of you are probably looking at this saying, well, no kidding, that's not really difficult to figure out. But again, I'm going to ask you to do the math here, and I'm going to ask you to set it up just so you can kind of get in the habit, because they're not always going to be simple problems like this, I promise. So we're going to start with what's given, 20 moles of carbon dioxide. This is going to be a one-step conversion. I'm going to put moles of carbon dioxide on the bottom, because again, I want that unit to cancel. I'm trying to figure out how many moles of lithium hydroxide I could produce, or I need to go along with that. Sorry, we would be figuring out how many moles we need to react along with that. And this is where I would use the mole ratio. I would look here and say, okay, well, we need 2 lithium hydroxides for every 1 carbon dioxide. So I'd fill in those coefficients here. Taking the coefficients from the balanced equation, I see a 2 in front of the lithium hydroxide, so I put it here. I see a 1 in front of the carbon dioxide, so I put it there. I would cancel my units and do my math. 20 times 2 would be 40 moles of lithium hydroxide. And that kind of makes sense if you look back at the equation. You know, the ratio tells us that we need twice as much lithium hydroxide as carbon dioxide. So if we start with 20 moles of carbon dioxide, twice as much would be 40. We just did it down here by setting up the math using a mole ratio. Let's try another problem together. Let's look at the next one. If you take a look at this problem, you'll notice that it's a little bit different. Something's missing there. So if you read through it, it says ammonia, NH3, is widely used as a fertilizer and in many household cleaners. How many moles of ammonia are produced when 6 moles of hydrogen gas react with an excess of nitrogen gas? So the first thing we have to do, hopefully you figured out, is to write a balanced equation. So it says how many moles of ammonia are produced. So are produced, that means that the ammonia is going to go on the product side. And it says 6 moles of hydrogen gas, which that's a diatomic, react with an excess of nitrogen gas. So then the next thing we would need to do is balance this equation. So I would put a 2 here and a 3 here. That gives me 6 hydrogens on each side and 2 nitrogens. Now I'm ready to start the problem. So I see that I have 6 moles of hydrogen gas. So let me switch my pen color here. 6 moles of hydrogen gas, and it says how many moles of ammonia are produced. So what's given is 6 moles of hydrogen gas. I'm going to set up my mole ratio. I'm going to put moles of hydrogen gas on the bottom. I'm going to put moles of ammonia on the top. The hydrogen gas goes on the bottom to cancel out. The ammonia goes on the top because that's what we're looking for. I'm going to go back to the balanced equation and look at the coefficients. I see that for every 3 moles of hydrogen gas that react, I can make 2 moles of ammonia. So the 3 comes from here and the 2 from here. I'm going to cancel my units. 6 times 2 is 12, divided by 3 is 4 moles of ammonia. So that's a one-step mole ratio problem that I just taught you how to do. What I'd like you to do is go to your packet and find a worksheet that says 9-1. 2 pages in your packet, 9-1, and I'd like for you to give that a try, and we'll go over the answers when I see you tomorrow.